So let me get going without any further ado. So first of all, thank you, Linaro, for organizing this and inviting us. And I hope that everybody's enjoying the day, and I hope that everybody's safe. I think this is a wonderful way of still continuing to do this, to have some fun together and geek out in technology, even during these challenging times. So my name is Markku, that's my face there. I'm a solutions architect at Google Cloud. I focus in IoT and machine learning and AI. I'm based in Tokyo. And today I'd like to show you about machine learning and AI at the edge. If you're wondering about the accent you're hearing, it's because I'm originally from Finland, even though I'm now in Tokyo, and the accent is called Rally English. So there's some historical backgrounds there. People got familiar with the accent with some rally legends. That's not me though, but some of my compatriots. Now at Google Cloud, so I've been in cloud computing about more than 10 years now, and I'm at Google Cloud now. My role here is a solutions architect, so I'll do my best to help our customers and communities, anybody who's interested in building something useful and interesting, using Google services, open source, and other products, putting them together in a hopefully meaningful way. But today, I would like to talk to you about AI, and specifically how we could leverage AI technologies at the edge, meaning with physical world devices. And before we start deep diving into that, I'd like to show you a couple of things about Google's AI principles. So some time ago, Google published these AI principles. So whatever we do as Google related to AI, we will follow these principles. And we are hoping that also other people and organizations follow similar principles, because we believe these are useful going forward. So they need to be socially beneficial, whatever you do with AI. You should not have any unfair bias. That takes some attention. So when you use data, when you have raw data, and then you want to use AI to get value out of the data, excuse me, even though AI is often a black box, you need to understand why the AI model is doing whatever it's doing, why it's giving certain results. It's very important so that there's fairness, equality, etc. if and when those results are used for any decision making. Of course, AI should be used with safety in mind and accountability. People's privacy should be honored. Of course, it's good if we have high standards of scientific excellence, and of course, if Google and our communities at large can also help improve and raise this scientific excellence. And then it should be available for everyone. So as much as possible, AI should be used then to democratize extracting value from data using these new programming methodologies that are called machine learning and AI. So what is AI? Well, it's many different things, but at its core, AI means that you don't anymore program the software with classical programming logic. Classical logic being, if my data looks like this, then do that. Else do this, or you have a case statement. That doesn't really work anymore with massive amounts of data, with very unstructured data like video streams and images and etc. So it's very difficult for humans to anymore program this kind of procedural logic to process that kind of data. Machine learning and AI is better for that kind of random data, if you will, because there the computers are learning in a similar manner as humans learn. The AI models or neural networks are exposed to data. They are exposed to training images, they're exposed to training data, and then the neural network basically enforces any patterns that it finds in the data. And quite often, the neural network can actually see patterns in the data that humans just cannot see. We cannot see the patterns in this random mess of binary numbers, etc. But at its core, AI means that you train the neural network with example data. So these are pictures of cats, these are pictures of dogs, etc. Or these are pictures of puppies, and these are pictures of muffins. So after a while, when you give hundreds, then thousands, maybe even millions of examples, the neural network will enforce the learnings, and it will then learn to distinguish, or in this case, classify between pictures of puppies and pictures of muffins. And you don't need to figure out how to program the model to do that. It gets even more difficult when you start to compare some doggies and mops. But nowadays, it is definitely possible to train neural networks and AI models that are significantly faster than humans, of course, at classifying or detecting objects in the data. And also the accuracy is significantly higher. At the end of the day, we have data scientists, we have people with PhDs in statistical analysis. I'm not one of those. So we have the experts who can build machine learning models by hand, the hard way, using frameworks like TensorFlow that Google open sourced and many other ones. However, we believe that as technology and the software ecosystem and hardware, everything advances, you don't necessarily need to know how a microwave oven works. You just need to put your food in the oven, press a button, and trust that the oven is heating up your food and not exploding it. So going forward, for most people concerned, you don't necessarily want to know how to create a neural network. You just want to enjoy having neural networks that are helping with your data and giving you reasonable responses. So if you will, the trend is towards moving to give me machine learning, please, by pressing a button, if you will. So machine learning as a service, easy machine learning, easy AI, makes it much more accessible and also democratizes the creation of machine learning models, which means that more people can use it. One way Google helps to do this is with our Coral platform. And this is something we launched almost exactly 1 year ago at Google I/O conference last year. So what is Coral? Coral is an open source ecosystem by Google where we have hardware, software, and development ecosystems that help you develop machine learning models and AI and then run them on your hardware. And why is running AI on hardware beneficial or necessary? Why do we need edge AI when we have massive clouds like Google has? We have massive data centers producing Google services, and you can also enjoy using Google's data centers through Google Cloud Platform. Now, of course, that's very useful and that's very common, but in some cases, you will want to run AI on your hardware at the edge. There are many reasons to do that. One of them is privacy. Depending on the type of data, maybe some medical data, etc., or depending on your location where you are, your legislation, your regulatory compliance, you may not always be able to upload or transfer your raw data up to the cloud, because that means it may leave your country or even it may leave your premises. So sometimes for privacy reasons, you need to process the data with your own devices at your premise. Latency is another consideration. Even though the cloud is relatively near, especially if the data centers are in the same country or nearby countries, there are some milliseconds or some tens of milliseconds to the cloud data centers and services there. Sometimes those tens of milliseconds may be too much. If, for example, you use AI with self-driving cars or some traffic monitoring or some other situation where you really need to have millisecond response to anything that you detect, especially if human safety or other kind of safety implications are involved. So if you consider a self-driving car that is driving 65 miles per hour, which is about 100 kilometers per hour, 100 milliseconds is about 10 meters. 10 feet? No, 3 meters. 1 foot is 3 meters. US measurements, imperial there. But you get the idea. The faster the object moves, the more critical latency becomes. So for example, for self-driving cars and similar use cases, you need to run the AI model on the edge, on the device. Another consideration is bandwidth. More and more you have high-resolution cameras with high-resolution images, even video stream. Transferring that video stream to another data center from a device can be very costly, and you know that if you have a mobile device, that connection may be disconnected at times, so you may not want to do this. Offline, you may want to have the AI model still running, even if you lose internet connections for production inference. And then, of course, cost. So sometimes, especially for the internet connection and large data volumes, high resolution data, it may be cheaper simply to run the machine learning inference on your device without any data transmission or storage costs. So in order to actually accelerate running AI models on your devices, Google has built some specific hardware. You may have heard of TPUs, or Google Tensor Processing Units. They are specialized chips that we are running in our data centers to run machine learning models in Google data centers, both for Google services like Google Photos, YouTube, etc. Basically, all the Google services are running AI to improve the customer features and make the service better. And then you can also run AI with Google services like Google Photos. If you upload your pictures to Google Photos, then you can do human language searches like, show me a picture of myself and my wife or girlfriend at a beach in Malaysia. So then you can use AI to basically query, for example, your images. Now, these kind of AI actions are then running on these large TPUs in the Google data centers. Now, those are only in the data centers. They are very big, they are very expensive, they require cooling, etc. So that's not really useful with something like IoT devices that need to be small, cheap, low power. That's why the Google Coral platform introduced the EdgeTPU. So it's a small, little TensorFlow processing unit. So it's a small ASIC that Google has designed and built specifically for running TensorFlow machine learning models on your device. The first version, which is here, of course, we have a roadmap of next generation versions. The first version that's commercially available now for anybody to try and use has 4 trillion operations per second at a maximum power utilization of 2 watts, and it's running quantized machine learning models, meaning that instead of floating point TensorFlow models, you quantize the model to integer calculations, which means that it's lighter for the small chip, it's more efficient, and it's faster. And then you can embed this EdgeTPU on your hardware if you want. And to start prototyping, Google Coral has some prototyping hardware that you can use for prototyping and developing these TensorFlow models and running them on the EdgeTPU. One of the hardware is here, and today in my presentation, I will be using this Google Coral development board with some live demos where we run machine learning and AI on that EdgeTPU chip using this board that you see on the screen. It's here on my table now. If you're interested in prototyping with Google Coral, you can order these development boards or PCI Express accelerators that have the same EdgeTPU inside. There's a USB 3 stick version, and then a system on a module. The one on the left, the development board, is something similar to a Raspberry Pi 4. It's not a Raspberry Pi 4, but it's similar to that. It's designed by Google, but the hardware specifications are very similar to a Raspberry Pi 4. It has an NXP IMX quad-core Cortex-A53 ARM CPU. It's running Debian. It's running a derivative of Debian called MendelOS, and it has the Google EdgeTPU coprocessor for running machine learning models next to the CPU. So the machine learning model will run on the TPU, and the CPU, the ARM CPU, runs the Debian operating system then. There's a cryptographic processor from Microchip that you can use to run any cryptographic operations and, for example, store your private keys for cloud connectivity in this secure trusted platform module. It has the latest Wi-Fi connectivity, gigabit Ethernet. It has the same 40-pin GPIO connector as a Raspberry Pi, so you can easily attach some other peripherals there, USB-C, HDMI, etc. So consider this board to be a prototyping board if you want to start running machine learning models on the edge using the EdgeTPU accelerator. The other option then is this USB stick. So it has a USB-C connector with USB 3, so you can plug it into any, for example, Linux device and simply start running machine learning models on the EdgeTPU on this USB stick. Now, if you want to try running machine learning models on your hardware using the EdgeTPU, basically, we have provided a software toolchain. Now, there's a lot of services that Google Cloud has to make it easy to develop machine learning models like AutoML, more about that soon. Or you can develop your TensorFlow machine learning models by hand if you're a data scientist. Then what this tool chain allows you to do is to go from your familiar TensorFlow models and then translate or convert those to TensorFlow Lite. TensorFlow Lite is then running on this EdgeTPU. That is then the quantized, slightly smaller model with similar accuracy as the floating point full TensorFlow model. Then when you run this compiled TensorFlow Lite model on the EdgeTPU, our software stack then provides the compiler and then C++ APIs for communicating with the EdgeTPU hardware running and managed by this Debian Linux operating system. And then we have also APIs and SDKs for C++ and Python that all developers can easily then run applications, import the EdgeTPU libraries on, for example, their Python code, and then very easily run their machine learning model inference against the EdgeTPU with their model. And that's what I would like to show you now. Basically, a short example of how you can run your machine learning model on your device using the EdgeTPU and Python libraries in this case. So first you initiate an engine. So you create a detection engine object using our Python SDK. And then, for example, if you want to do image classification or object detection, you open an image, just standard Python here. And then with one line of code, you can run inference. So basically you call the engine object and it will have different methods. For example, one method will be detect something with image. And then you call this method, you give it your image object as the raw data. And then you tell earlier when you create the engine, what is the model that you want to run and what is the labels file. The model is the TensorFlow Lite model, the machine learning neural network optimized for the EdgeTPU. And the labels file contains the labels that you're classifying like cats and dogs and mops and bananas and oranges, etc. And then it's simply one line of code. That Python line that is highlighted on the bottom here then communicates with the EdgeTPU processor, runs the model with that image, your raw image, and gets back a response. This is the machine learning inference response. And then you simply, in your Python code in this case, you investigate the response. And for example, if you're doing object detection in an image, you will get the bounding box coordinates, and then you can draw a box around the object that was detected. So that was just a quick code example. But now, rather than boring you with slides and boring you with code examples, I believe some of you may want to see what this actually looks like. So why don't we now start using the Google Coral development board that I have on the table here. I have two cameras connected to it. One of them is here next to my webcam. There's another webcam connected to the board. And we could run a model that is detecting persons in real time in this video image. That would be me. And then applying privacy protection. So for example, obfuscating or protecting the identity of detected people. So for example, let's say that you have a venue and you have a maximum capacity of 70 people, just to throw a number. You would like to know how many people there are in this room so that you are within your safety and legal limits. So you could, for example, have a camera monitoring, taking live feed of this venue, but then detecting people and counting how many people there are to know that you are within your safety and legal limitations, but not exposing anybody's privacy, not violating anyone's privacy. So you could, for example, obfuscate the people, remove their identity. So let's see how we could do this using the precompiled posenet model. So posenet is one of the open source precompiled models. So let's run that model on the EdgeTPU. So you can see here on the screen that on my right-hand corner here, top right corner, we have a shell, and that is connected to the Google Coral development board. You can see that it's running Debian 10. And now, if I run the example application in Python, we run the MobileNet posenet model, and we execute it on the Google EdgeTPU. And this screen here is the HDMI output of the development board. So let me start running this model in 720p resolution now, and let's see what happens. So now you should see me. Well, you don't see me, you see the obfuscated version of me, and I do a very awkward engineer dance here. You can see that the posenet model is detecting a human, that would be me, but in real time, the EdgeTPU model is then telling the application what are the boundaries of the human, and then the Python application is simply painting over the human with red color, red pixels in this case, to protect the privacy of the person. And on the top of the screen, if I can point somewhere there, you can see current occupancy 1. So currently, the machine learning model is saying that in this room, there's one person, and we are also able to see their pose, if that's useful. But the main point here would be counting the number of people and then protecting their privacy with obfuscation. And that's happening in real time. And the overall processing time here is now about 40 milliseconds. And we are running about 25 frames per second. And the raw resolution of the camera is now 720p, so 1280 times 720. Okay, that was the first demo. Let's go back to the slides. So that was the Google Coral EdgeTPU and development board running the posenet model, and that was a pre-compiled model. Now, some of you may say, well, that's fine. We have a lot of pre-compiled models. How about custom models? For my business problem, I need a custom model. Yes, I fully understand. That's most likely the case. And I personally, I shouldn't have favorites, but I kind of have a favorite in the Google Cloud service portfolio, and that's this one, AutoML. Because I'm not a data scientist, I don't know how to create neural networks by hand. It's been on my to-do list for a couple of years now. But because of AutoML, I've been a little bit lazy. I don't have to know how to make a machine learning model. I just use AutoML to create a machine learning model for me. So now I'd like to show you how AutoML can help you democratize, make it very easy, very fast to create custom machine learning models. With AutoML, the funny thing is that we have machine learning models creating machine learning models, because we have come to the point now in technology that machine learning is better than humans at creating other machine learning. So basically what happens is that with AutoML, you give the system your training data. For example, you give pictures of your puppies and your muffins. You say, these are images of puppies and these are images of muffins. Figure it out. You press a button in AutoML that's called train. And what AutoML will do is that on the left side of the screen, it will create something called the meta learner. It will create a machine learning model, which goal is to create another machine learning model that is really good at classifying between puppies and muffins. So what AutoML will do is it will try so many different things that humans cannot keep up with that. It will try different models. It will do the hyperparameter tuning and optimization and selecting, and ultimately, it will train and identify and select the best performing model. And based on our testing, the model quality will be better than that done by humans in most cases. So let's see how we could use AutoML. So I live in Japan. I'm a big fan of sushi, but sometimes I forget, what is this sushi? What sushi am I looking at? So I was wondering, could I use Cloud AutoML to create a custom machine learning model to help me identify different types of sushi? So what I did was I bought some sushi, bought some little toy sushis that don't go bad so quickly. You can see them here on the screen. This is the console of Cloud AutoML. I took pictures of these little sushis with my phone. I took something like 300 images of each of these sushis. When you press the phone camera shutter button and you keep it down, with most phones, it will just take endless pictures, right? So I took these endless images of my sushis. I uploaded them to the service, and I said that this folder is full of ebi nigiri sushi photos, and this folder is full of ika nigiri, different types of sushi. And then in AutoML, all you need to do is to press the button that says train. You go for coffee or you go for tea, you come back, and the service will create a custom machine learning model for you that is able to classify, in this case, between different types of sushi, your sushi, so a custom model for you. And then how you can actually use this in the big picture is that you go from raw data, everybody has raw data, and most people have, and most organizations have more data that they can handle. Now, one way you can actually extract value from this data is with AI and machine learning, but you probably need a custom model. So then what you can do is you discover your data, you dump it into Cloud AutoML, and then you classify it. You say, these are puppies, these are muffins, these are fraudulent credit card transactions, these are good credit card transactions. You get the idea. You give it examples. And then if necessary, you can use also human labeling services. If you have a lot of images, for example, that are not labeled, there are services that you can scale with human workers or machine workers, excuse me, to label that data. Once you have a lot of examples of training data, what is a lot? Well, based on my personal testing and prototyping, if you have at least 100 examples of something and 100 examples of something else, that's a good starting point. 1,000 examples of something and something else is even better. So with machine learning training data, more data is good. Better data is good. So if you can have high quality data and a lot of high quality data, the end result machine learning model is even better. But then you don't need to know how to create a machine learning model, how to create a neural network. You let AutoML handle that. It does the feature engineering, model selection, hyperparameter tuning, and it will spit out your custom model. You can do the testing in the cloud to verify that it looks okay. Or you can export the model and, for example, then run it on the Google Coral hardware. We have services like Cloud IoT Core, if necessary, for transmitting data easily between devices and the cloud using constrained network connections. Ultimately, you transfer this model file, which is a couple of kilobytes, a few kilobytes, it's small, to your Coral device with the EdgeTPU or any other server which has the EdgeTPU connected. Then you run the model, you run the machine learning inference at the edge. And then what you can do is you collect the results and then you iterate. Just like with any software, you do iterative agile development of your machine learning model. So you can do retraining of the model, learning from mistakes, continuously improving the model. Anyway, let's now see this demo of the sushi model. So let's see if AutoML can help us create a machine learning model that can classify between my sushi, and then if we can run this model at the edge using Google EdgeTPU accelerator. So let's go back to my machine here. And what I would like to show you first is the Cloud AutoML user interface. So we are here in Google Cloud Platform. The service is called Vision, and Vision has a couple of options. We have pre-built Cloud Vision API, which Google has trained with millions of images to detect and classify standard objects like cars and cats. But if you need to classify between your two different cats, Bobby and Skippy, then the standard model will not know this. You will need to create a custom model. Or if you want to classify between your different sushi types, you will need a custom model. So this is what I have done. You can see these examples of images I took of my sushi. You can see that they have different labels. I have something like 7 different sushi labels here. Then you can press train once you have the training data in the service. You can click train new model, go for coffee. The system will send you an email when it's done creating the model, and then you can evaluate the model. Now, in this case, my confusion matrix or model evaluation is pretty positive because at least based on the testing that the service has done, it was correct in all cases of detecting. So when the system itself finished creating the model, AutoML tested the model against a portion of the training images. So portion of the images that I gave to the service were used for training the model, and a portion of the images were then used for testing, for verifying, is this sushi that is supposed to be epinigiri really epinigiri? So then these are the testing results, and at least in this case, the model was very successful because it didn't make any mistakes. That depends on your data and there are ways to improve the model. I will show you some of those later today. Anyway, we have the model here, and then what you can do is you can export the model. You can run it in the cloud, you can send your data to the cloud and just get the service result back. But if you need to run the model on your device, you can then export the model as a TensorFlow Lite file or TensorFlow JavaScript file, which is easy to run on mobile applications, or for example, Core ML or Container, which is very popular, or simply you can ask the service to give you a TensorFlow Lite file that is optimized for running on the Google Coral EdgeTPU accelerator. So then you can just export the file to your cloud storage and copy it from there to your hardware. So this is what I have done. So the next thing we could do is I could show you that on my machine here, on my Coral development board, I have the SUSE EdgeTPU model TensorFlow Lite file on my Coral development board. So we could use this model and then run live inference. So let's see what that looks like. So I will start a Python application on the Coral development board. And as you can see here, we will load this custom SUSE model and the SUSE labels file. And let's see what happens. We go back to the HDMI output. So now you can see the live picture of the Coral development board camera feed. And on the bottom right-hand side of the corner, you can see the current detected label or classified label. Ikura Gungan means Ikura is Salmon Row and Gungan is like battleship. So the system or the model is currently correctly classifying that this is indeed Ikura Gungan. If I change it, this is a Tamako nigiri. Now you can see that yes, the machine learning model is telling us that that is indeed Tamako nigiri. Let's try ebi. Now that's ebi nigiri. So look at the bottom right. Yes, that's correct. Let's put Tamako back there. Yes, Tamako nigiri. Tamako is egg and nigiri is this sushi on the bottom here. And then please take a look at the bottom left side of the screen here. The inference time is the milliseconds that the Google Coral EdgeTPU was running inference. So that is the machine learning inference time on the EdgeTPU. So it's something like 4 milliseconds. This is now running at 720p resolution. And you can see that the frames per second is currently about 220, 230 frames per second. So definitely it's fast enough for real-time inference using the EdgeTPU with high resolution source video feed in this case. Okay, so that was the SUSE model. And here we can see the AutoML console. So it's this model that AutoML created for us. All right, let's move on. So that was the second demo, running EdgeTPU custom model created by AutoML. Now somebody will say, yeah, demos are cool, technology demos, smoke and mirrors, whatever. We live in the real world. How about the real world? Yes, I hear you. So what I'd like to show you next is an actual customer case. So I was working in this customer case as a team member with Kyocera. Kyocera is a company in Japan. The word Kyocera comes from Kyoto Ceramics. So it's a traditional company, well-respected company in Japan, focusing in ceramics. They make, for example, nice ceramic knives. And Kyocera are producing small and medium batch manufacturing for other companies. And they wanted to see if Google technologies, Google AI, could help them with quality control on their manufacturing lines, basically visually inspecting objects. What you can see here on the right side is an animated GIF of the actual raw images from the Kyocera production line. So you can see here that these are the objects they are manufacturing. So there's a camera on top of the production line, the conveyor belt, and the object in the middle is one of those objects they are manufacturing. You can also see partially other objects on the same tray. But what we are interested in doing here is detecting any faults, any issues with the center object there. And these are actually examples of broken objects. We know they are broken. Kyocera told us that these are examples of broken center object. So you may see some little blips like black dots sometimes on the center object. Those are the faults, the defects that we want to find with AI. Now for machine learning, there's a couple of challenges here. The first challenge is that there's multiple objects visible, we should be focusing on the center object. Then the center object is moving around, and the defects are really small little blips in this moving object. So there's a lot of confusing signals in these raw images for the neural network. So the neural network doesn't know where to look. So basically we have a problem of signal to noise ratio being wrong here. The signal of the actual faults is very small, but the signal of the object jumping around in the middle is very strong. So as a result, when I tried using AutoML first with these raw images that you saw in the previous page, the worst case quality, worst case scenario of the machine learning model success was 14%. So that's not good at all. So definitely we needed to do something to get the model quality better than 14%. It's not usable. So what we tried to do was a bit of data pre-processing. So before we give the data to Cloud AutoML as training data, we wanted to clean up and help manipulate the training data so that the neural network can focus on finding the defects in the objects. So the first step we did was to cut or crop the raw image and cut away, if you will, the exterior objects that are not relevant here. By the way, here in the highlight, you can see one of those defects. So it's really small there. So that's an example of a defect that we should find with the AI model. The second step was that I wanted to remove the background pixels from the image. I wanted to basically turn the background pixels black or remove them so that the only pixels remaining in the image belong to the object we are trying to detect. So I applied some image filters and I got rid of the background. Next, I applied another Python image filter that gave us a point cloud of the object's edges. But those are not lines, those are just dots. Next step, I applied something called Hoff transform, which is then looking at this point cloud of edges in the object and detecting if they are continuous lines. Why do I do this? Because I want to know, is the object rotated in some angle, and where is the object? So two things, where is the object and is it rotated at an angle? With this Hoff transform, we can get the lines, and then I can calculate the rotational angle of these lines. And then I can simply counter-rotate the object back so that those lines are horizontal and vertical, 0 degrees. So we can use these detected object lines to rotate the object back horizontal. Then I run one more round of filtering, getting the image edges, and then I can crop on the bounding box of the rotated found object. As a result, after this pre-processing, this is what the training images look like. We get rid of the confusing background. The object is not jumping around anymore, and it's stationary. So now the only changes between the images should be those defects. And as a result, when we then gave these images, you can see a sample of these processed training images that we gave to AutoML. Now the model quality was 95 and 98% successful at detecting good and broken objects. And the EdgeTPU performance test was 8.9 milliseconds on average. So minimum 95% accuracy at 9 milliseconds latency. So now, with the remaining couple of minutes, I would like to show you a live demo of exactly this, the Kyocera customer case. So here on this bottom window here, bottom right-hand side console, we can run the pre-processing first. So I'd like to show you, this is one of the raw images from the Kyocera production line. You can see the object in the middle. It's rotated at an angle. There's a lot of confusing stuff on the outside. So let's see how this pre-processing pipeline could help focus the data a little bit better. So I run this pre-processing pipeline, and you can see that we wrote an output file. You can see this was run in debug mode, so you can see the interim steps here, like removing the background, doing the Hoff transform, finding the lines, rotating the object, and then finally, this is the end result. The focused, rotated, fixed object. When we gave these to AutoML, it gave us this high quality machine learning model. And then on the Coral board, what we can do is that we can run a test. So I have the model here created by AutoML with these pre-processed images. You can see here, SDM is this Kyocera model. And what I'd like to do now is to run a performance and quality test using this Kyocera AutoML created model against example images from the Kyocera production line. Let's first run this machine learning model against known to be good examples. So all the images in this next folder that I run are known to be good. So let's see what the machine learning model is telling us. So now one by one, we are processing these raw images. You can see the image name on the left. And then the second column here, you can see OK, is the machine learning inference result or classification result. So it's saying in all these cases that this object is OK. However, I want to find a mistake here. Not so you can see the highlight, but I highlight one line here in the output. Here we have one example where the machine learning model made a mistake. It said that this is a broken object when we know it's not, because Kyocera told us that these are examples of good objects. However, when we look at this mistake, machine learning is not black and white. It's not usually 100% and 0. Here we have a mistake, but when you look at the next column, that's the confidence. With machine learning, when you call inference, you get a confidence, you get a label, for example, not good in this case, and then you get a machine learning confidence. Here it's only 50%, so it's very low confidence. If you look at the other results, you can see 84%, 88%, 83%. So what you could do, based on your testing, of course, and your situation, is have a threshold that I don't trust results that are lower than 80%, for example. What do you do with those results that are lower than 80%? You put them aside, you investigate them, and you probably use them to train a new model until your model gets better and better. So I just wanted to show you a mistake as well. Next, very quickly, let's run the same model against all the known to be bad components, broken components. So now you can see that in most cases, the model is saying not good, not good, not good. So that's correct. They are not good, but actually the last example was again a mistake. The model said that, yeah, that's a good component when we know it's not, but again, the confidence was low at only 50%. So that was an actual test of the Kyocera manufacturing visual inspection model against both good and bad objects. And you can see that in most cases, the machine learning model was correct in 95 to 98% of the times. There we go. I really hope that you enjoyed it. And just to show you what we actually ran here, we ran the model on this Google Coral development board. It's a prototyping board. Under this heatsink there is the EdgeTPU processor. We executed the pre-processing with the CPU. So for example, if you run it on the board, you can use the ARM CPU to do the image pre-processing. And then you can use this EdgeTPU then to run the image that you want to classify. You run the inference on the EdgeTPU accelerator, and you run the neural network inside the EdgeTPU processor, and you get a classification result. In this case, in the demo that you saw just now, you simply get a label, OK or not good. So that's what the machine learning model will tell you. That's all I had today, except one more final thing. Somebody will remind me again that, yeah, it's good, but the model is not static, so model is software. That's right. Machine learning is also software, just like any other software. So you need to consider things like lifecycle management. You need to consider deployment of your model at scale. After prototyping and testing, if you go to production, depending on your use case, you may have hundreds, thousands, or even millions of devices out there in the field, all running maybe different versions of machine learning models. So you need to know what is out there, you need to have visibility, and you need to have efficient and reliable deployment mechanisms at scale, then to manage this fleet of devices and machine learning models. So then you get into a topic called ML ops. So that's one new thing in the world of IT now. You need to have ML ops, basically having CI/CD pipelines, continuous integration and deployment, agile development of machine learning models, collecting also the inference results from testing and even from production if you can, using that data to train new models, test the new models against old models, replace with the better model, and continuously iterate until your model is exceeding your business goals and giving you the result that you need. There we go. I really hope that you enjoyed the show. That's my Twitter handle there, slightly too long due to my Finnish name, Rally English. Thank you very much.
Great, thank you, Markku. We actually have a question here in the chat. So
sure.
As we've got some time left, the question goes, is it possible to integrate Google Coral features in Yocto Project OS?
I haven't personally used Yocto, so we have Mendel on the Google Coral boards, but however, you can take the EdgeTPU in different form factors like system module or PCI Express, etc., and integrate it to your Linux server. Absolutely, it should be possible. Yocto is just yet another Linux. So the question is, do we have pre-compiled packages? You know, Linux has package management, right? Debian has easy apt-get package management. Whether we have Yocto packages with the SDKs already or not, or whether we need to compile those from source code, that I don't know. Our Coral product line would know. Definitely it will work, but we may need to do this binary compilation for Yocto first. But if there's people who need that for Yocto, please let us know. You see my Twitter handle there. My email is markku@google, my first name markku@google.com. So please let me know and I can connect you to those people at Coral then.
Okay, and we've got a few more comments here. So the next question is, what are the plans for making the Coral's bootloader EBBR compliant for booting other OSs?
Well, the Coral development board is a playground machine. So it has the Mendel operating system. It comes from the Google product line. So we maintain the operating system image. We've built the bootloader, the optimized Mendel OS, which already has all the packages and drivers for EdgeTPU, etc. So that's an easy way. But if you want to customize things, you can. It is a standard Linux server running ARM. So all these things can be absolutely customized. But the point of the Coral development board is to give you a really easy prototyping platform. But you can just take the EdgeTPU in many different form factors and integrate it on your hardware. So that's actually likely going to be the production method. So this development board is not probably going to be in production. It's more for testing and prototyping.
Okay, great. And I think we've got time for one more question. So are there things in Mendel that it would be useful to upstream into Debian, or is that already happening?
That's a good question. I don't know how the forks are going back and forth. So Mendel is a derivative of Debian. So Mendel is part of the Debian family. You know, there's Mint and Ubuntu. Somebody may not like me saying that, but Debian is the father or mother of all those, right? So Mendel is a Debian-based distribution. Whether the teams are contributing back to the main, I don't know. That's a good question, but definitely it's an open source derivative of Debian. But how the contributions go, I personally haven't checked that.
Okay. And sorry, one more question. We've got 2 minutes. So what's the FPS of the camera that Coral can process?
Well, Coral has its own camera. It's similar to the Raspberry Pi camera. So it's got the similar kind of connector. It's not the Raspberry Pi camera because it has autofocus. The Pi camera doesn't. So in this case, what I did personally is that I used the Coral AI camera, which is the small camera module. That was for the sushi demo. And then I had a Logitech webcam connected over USB for the posenet where you saw me. So I had 2 different cameras there. So basically, it's just a matter of the camera module you use, the interface you use to talk to the camera, and the bandwidth available there. So there's no one answer for that, but definitely I have seen, like in this demo that you saw, it was running 720p with raw video feed from the camera, and it was running about 240 frames per second. I don't know what is the maximum, but it's very high.
Okay. Great. Well, thank you so much, Markku. That was really interesting and lots of good questions. And as you said, if anyone else has any other questions, you saw Markku's Twitter handle, and sorry, do you want to add your email address in the chat in case there are any other questions, if you're happy to
Yeah,
receive
absolutely.
questions?
Give me just a second. Okay. Hi all. Yeah, markku@google.com. So just ping me, and then I will be a bad router, routing messages to a Coral team after that.
Excellent.
I'll do my best.
Great. Thank you so much, Markku. And yeah, thank you very much.
Thank you, everybody. Bye-bye.